Hello, welcome back to Flipped. Today we are on the mole concept and stoichiometry, and this is a learning objective for today. We are defining the terms relative atomic, isotopic, molecular, and formular mass. So this is just a quick recap. Elements are substances that cannot be decomposed into simpler substances. They exist as either atoms or molecules. Okay, so this is back to our O-level syllabus, okay, which is a high school syllabus. Basically, we are saying that elements can either be, for example, argon. Okay, you cannot break it down into simpler form, or it can also be chlorine too. Okay, although this has 2 units of it, but this is the simplest form. Okay, so this is the element form of substances. They can also exist as compounds, which are a combination of elements in fixed ratio. Okay, so the keyword here is fixed ratio. Okay, so for example, we have okay, they can exist as either ions or molecules. So in terms of ions, they can be, for example, our favorite NaCl, sodium chloride. They can also be in terms of molecules like hydrogen chloride. Okay, so you can see that these are fixed ratio. Okay, there's one H and one Cl, one Na, one Cl. Okay, and these are combinations of elements. They are mixed. They are made up of different elements. Okay, in this case, sodium and chloride. This case, hydrogen and chlorine. So ions can be positively charged or negatively charged, whereas atoms and molecules have to be neutral. Okay, as we can see from here, Na has to be a plus, Cl is a minus. So this is what we mean by positive and negatively charged, whereas atoms like such and molecules as HCl are neutral. They do not contain any charge. This is the first one that we want to explore. It's relative mass, which is talking about an atom, a molecule or ion, and is obtained by comparing its mass with the mass of one atom of carbon-12 isotope. Okay, what do I mean by this? This is the formula. So what I'm saying is that if I want to find out the mass of any substances, any particle, I'm just going to take that particle mass, okay, divide by 1/12 of the mass of one atom of 12C, carbon-12. What this essentially is, because let me just do a very quick working for you. We know that 12C is written like this, 12. Okay, this is the mass C, and this is the proton number 6. So we know that the mass of carbon is actually 12. And if I take 1/12 times 12, okay, you can see that. Okay, let me just write it here. If I take 1/12, maybe this is not good color. Let me change it to something brighter. 1/12 times the 12 that I'm obtaining here, okay, it actually gives me, what do you think? This becomes 1, right? Because they can cancel each other out, and gives me 1. So essentially, what I've done is I'm taking the mass of whatever particle I'm measuring divided by 1 here, okay? Because this part, the bottom part, okay, works out to be 1 because I'm using 12C as an a base to be compared with, and hence whatever mass I have for the particle is my relative mass. Okay, and because it's done in this way, it's actually a ratio, and that's why it has no units. Okay, this is a very layman way of explaining, but I hope this makes sense to you. What I'm doing is that I know 12C is being used, so 1/12 times 12 is 1. Whatever mass of my particle is, be it an atom, a molecule, or ion, whatever it is, I'm using that to divide by 1, and that is my relative mass of my particle already. Okay, so this formula applies for many things, okay, which we will see right now. Before we move on to the calculation of isotopic, molecular, and formular mass, I want to talk about something called isotope. Okay, recall that isotope are atoms with the same number of protons but different number of electrons. Some examples are, for example, 16O. Okay, this is oxygen. Can also be 17O or 18O. Okay, so these are 3 different isotopes of oxygen. Another example would be bromine, which is 79 Br, or it can exist as 81 Br. Okay, so these are some examples of isotopes. Basically, they have the same number of protons, but different number of neutrons. Okay, same protons because they have the same elements. Okay, this thing called abundance of a specific isotope is saying the percentage of particular isotope found in an element. For example, I know that oxygen exists, okay, can exist in 3 different isotopes. Okay, but I want to know that how much of it exists as 16O, how much exists as 17O, and how much exists as 18O. For example, I just assign a random number to it. In terms of 16O, maybe it's just 50%. 17O, maybe 25%. and 18O is also 25%, for example. Okay, and this is the abundance really. Basically, abundance of 16O is 50%, 17O 25, 18O is 25. So this is what we call abundance. Another example the textbook gives us is abundance of 35 Cl. Okay, it's 75%, which means that 75% of all Cl atoms are 35 Cl. Okay, hopefully this makes sense. It's really just how much of a particular isotope are found in the element. Because in the A-level syllabus, we know that elements do not exist as simply as what we see in the periodic table. They are made up of many isotopes. Okay, and this is called the abundance, which is just a percentage. So moving on from isotopes, there's this thing called isotones and isoelectronic. Basically, isotones are atoms with the same number of neutrons. Okay, so some examples I can give you are fluorine and neon. Okay, so if you go and calculate them based on the periodic table, you will see that they have the same number of neutrons, although their proton number are different. Isoelectronic is the same number of electrons. So one example I can give you is neon and sodium, but with a plus sign. Okay, it has lost one electron, so it can gain the same number of electrons as neon. Okay, you can check it out if you want to. So in short, we have covered three things in this slide. Isotope is same number of protons but different neutrons. Isotones is same number of neutrons. Isoelectronic is same number of electrons. Okay, iso means same. Okay, if that helps you. So this is talking about relative isotopic mass. Okay, we are talking about the second one now. Okay, of an isotope is the number of times the isotope is heavier than 1/12 of an atom of carbon-12 isotope. Recall that 12C is written as such, 12C6. Okay, so if I'm using this 1/12 times this 12, it'll give me 1. So whatever mass of my isotope I have here is my relative isotopic mass. Okay, it works the same way as the equation, as the formula we've seen in the first slide. Okay, hopefully this is useful for you. And because it's a ratio, okay, it has no units. Okay, whatever mass you have, you just write it as such with no units such as grams or kg, even though it's called mass. Okay, it has no units. Similarly, relative atomic mass, we have actually seen this in O-level syllabus, okay, the high school syllabus. Basically, relative atomic mass is talking about elements, and is the weighted average of its atoms in the naturally occurring isotopic mixture, comparing 1/12 mass of an atom of carbon-12 isotope. Okay, so this formula actually looks very complicated, right? It's very different from what we have seen, but actually it's not any different. What I'm talking about is remember our three examples. We have, for example, not 17O. We start off with 16O. Am I right? 16O and 17O and 18O. Remember our example for this? Okay, then we gave them an arbitrary abundance. For example, I will say that 16O exists 50%, 25% for this guy, and 25% for this guy. What I'm talking about is when I get the abundance, I multiply by their mass. Okay, for example, half, 50% times 16. 1/4 times 17, 1/4 times 18. And I add this all up. Okay, I add this three guy. Okay, there are three separate components, right? When I add these three up, I get the top portion here. The bottom portion, as usual, it's 1/12 times the mass of one atom of 12C is 12. So it's just nice, it gives me a number of 1. Whatever mass I have on top gives me, divide by 1, gives me my same number here. Okay, so this formula actually is the same. It's just that this sign may this sign may confuse you. This sign is actually called a sigma. This is a sum of everything. Okay, this is a sum of sign. Okay, maybe I just write it down for you. This guy is a sum of, okay, everything. Okay, sum of 16O plus sum of 17O plus the sum of 18O. The whole thing gives me this top portion here, the numerator. Okay, so you can see that this formula is the same as what we have seen before. And because it's a ratio, it has no units, the same. So what we see here is MR, which is relative molecular mass. Okay, I'll give you a summary later about AR and MR in the next slide. But MR, as we have learned in O-level as well, high school, is that it's for molecular substance, and it's the average mass of one molecule of substance compared to 1/12 of a mass of an atom of carbon-12 isotope. Okay, so it's the same thing as before. The denominator, okay, the bottom part I would explain because it's the same as previous slides. Top part is really just the average mass of one molecule of substance. For example, my substance is HCl. Okay, I just have to add the mass of the AR, okay, AR of H plus the AR of, okay, AR of Cl. Okay, when I add them up, this is the MR of HCl. So basically, what I'm trying to say is that MR is the sum of all the ARs of the elements present. Okay, because H is present here, Cl is present here. When I add them up, this is the MR. Okay, makes sense, right? So this is the average mass of one molecule of the substance. This guy here, I plug it in on the top and divide by this number, as you know, will be 1. And I'll get my relative molecular mass, which is called MR. Okay, so this is just this is a working, correct? But usually we do not work this out. We just have to obtain a number, okay, from the periodic table. And as usual, relative mass is a ratio. It has no units. This slide compares what's AR and MR. Okay, AR is relative atomic mass, is for one element. Relative molecular mass is for a molecule. So an example I will give you is Cl2. MR, an example I'll give you is HCl. Okay, so this makes sense, right? So this is for element. Okay, this is for molecule. Molecule because it is made up of more than one element. Okay, it's made up of two elements in this case. Okay, so what about ionic compounds? We reserve ionic compounds, okay, with this formula here. This is called relative formula mass. Okay, it's the average mass of all atoms in a formula divided by, okay, as you know it, this is just 1. Okay, this is the definition. Relative formula of an ionic compound is the average mass of all the atoms in a formula compared to 1/12 mass of an atom of carbon-12 isotope. So it's the same thing. Just that you may ask me, so what's the difference between this and relative molecular mass? I would say the only difference is that because this is reserved for ionic compound. Okay, I want to calculate, for example, the relative formula mass of, say, NaCl. Okay, I technically cannot call this a molecule. Okay, so I have to use this formula instead. Recall that the previous formula, relative molecular mass, is for molecules, right? Because that's why the name is called molecular. And so I cannot technically use that formula for NaCl because NaCl is an ionic compound. It's not a molecule per se. Okay, so I have to use this formula instead. But this formula works exactly the same way as molecular mass formula. So what I'm trying to say is that I will get the AR of Na to add on to the AR of Cl. And this will give me the, okay, I'll put a open quotation here, MR of NaCl, okay, which is the relative molecular formula mass of NaCl. Okay, so the difference between this and molecular mass is really just that this is technicality. Okay, NaCl is an ionic compound, so I cannot use a molecular formula for it. Okay, and that will be all for this this portion, which is to define the terms relative atomic, isotopic, molecular, and formula mass for this chapter of mole concept and stoichiometry.